First of all, I would like to thank the organizers, Begoña and Maria, for this opportunity to meet in this particular situation. So thank you a lot. So in this talk, I will discuss some facts about elliptic equations with first order terms. So first I will give some motivations from both applications and the mathematical point of view of elliptic equations. And then I will discuss the fractional model, some related results, and finally I will give some contributions, applications, and consequences of the main results. So let me start with an application of elliptic equation with first order terms. So let's see first the parabolic part. So suppose that we have an evolving surface, right, or a growing surface. So as you see, growth in this surface takes place at least locally in the normal direction to the surface. But if we project the growth into the lateral direction, let's say h. So I will go back to the picture. So you have here the growth in the normal direction. So if we project into h, what we have here is that the increment in the height of the point can be expressed as the square root of this quantity here. So this is just Pythagorean theorem. So this guy here, this nu, is the speed of the growth of the surface in the normal direction. So if you divide these quantities by delta t, and then let delta t go into 0, what we have here in more dimension is a parabolic equation where in the square roots we take a Taylor expansion. So here we have the nonlinear first order terms plus some other terms here. And also if we minimize the gradient, then we have the Laplacian here. So this is a model called the KPC model for the growth of surfaces. And as you see here, we have the Laplacian, and also we have nonlinear first order terms. So indeed, this kind of equations have some interesting facts. Indeed, at least formally, I will talk about this later, but if you perform the Hopf-Kohl change of variables, so you call V this quantity, then this equation or the equation that we solve is this one here, which is a linear equation that appears in the model of growth for brain tumors. Also, again, formally, right? So if you derive the original equation and you call bi the partial derivative of u with respect to xi, then you obtain the Euler equation without pressure, which is the equation here. Okay, so now I would like to discuss some problems, elliptic problems with first order terms, and give some motivation from the mathematical point of view of studying this kind of problems. So first, let's take a simple model, which is this one here. So you have the Laplacian, a quadratic term in the gradient, and then here we have a source that we write lambda times f. So the function f would be non-negative. And what we have here is that the presence of nonlinear first order terms impose some restrictions in the size of the source in order to have solutions. So indeed, if lambda is small enough, and if the function f is in Ln/2, then there is a unique solution of the problem with this regularity. In contrast, for sufficiently large lambda, there is no solution of the problem with this regularity. Indeed, Abdelawi, Dallaglio, and our friend Ireneo Peral, they prove that if the function f is locally integrable, and if there exists a smooth function compactly supported in omega, so that this inequality holds, then there is no solution of the problem 1 in the larger space W120 of omega. So it makes sense to consider this quantity, this variational quantity, and indeed to impose the condition first that lambda 1 is positive. So in that case, the function f is indeed in the dual space of W120. And moreover, in the same paper that I quoted before, they found that there is no solution of the problem. Problem 1, let me recall you, problem 1 is just this one here. So there is no solution if lambda is bigger than lambda 1f, and there is a unique solution in the space so that the solution has this regularity if lambda is smaller than lambda 1f. So the contribution of this paper is that they gave the exact value of lambda so that you have solution or not. In addition, they also proved that any solution of the above problem with f in L1 satisfies this regularity with a delta which is less than 1/2. So any solution has at least this regularity, and indeed this result is sharp. Indeed, if you take the homogeneous problem with f equals 0 in the unit ball in Rn, this family of solutions satisfy this. So they don't have the regularity with delta equals 1/2. So this result is sharp in that sense. Okay, so as I said, if you have first order terms or nonlinear first order term in the equation, then usually you have some restriction in the size of the source in order to get solutions. So let's see now the relation with measures, relation of this problem with measures. So let me just recall the definition of a measure concentrated on a Borel set E. So we say that the radon measure is concentrated on a Borel set E if the following holds for any Borel set A. So a first result that shows a relation between the problems that we discussed and measures is the following. So suppose that you have a solution W120 of the problem that I showed you before for non-negative f in L1. Suppose that you take the Hofstadter transformation. This is I discussed in the beginning. Then this transformation of U, this change of variables, satisfies this regularity. And moreover, there is a measure mu concentrated on a set of 0 capacity such that B satisfies this equation. So in the beginning, I say that at least formally, if you take this transformation of the solution U, then you get this equation without the measure. So this is the right result. And indeed, the solution B has this regularity. So the truncation of B lies in the right space for all k. Okay, so this is in order to answer the question of what happens if you perform this change of variables. Okay, but more can be said. If you take f in the space LR for r greater than n/2, and again you define lambda 1 in this way, and if you take any positive radon measure with bounded total variation, then this problem, which is the problem I showed you in the previous slide, then you have that this problem has a unique positive solution for all lambda smaller than lambda 1. Okay, so if you take this problem, then this problem has a unique solution, unique positive solution. So this problem is like easier to solve than the problem with first order terms. So the idea now is to take the log of 1 plus b, which is the solution of this problem, and then that function should be the solution of the original problem, which contains the quadratic norm of the gradient. So, and indeed, that's the case. So if you take any measure mu concentrated on a set of 0 capacity, and if you take f again in LR with R greater than N over 2, then if you take the unique positive solution of this problem and take the log of 1 plus that solution, then that function solves the original problem. Okay, so here we have some connection between measures and elliptic problem with first order terms. So finally, before starting with the fractional framework and our contributions, I would like to discuss another fact, interesting fact of having nonlinear first order terms in elliptic equations. So if you have this equation here with the Hardy potential, f a positive function in L1, with a 0 in the set omega, then in general, this problem has no solution. That was proved by Bocard, Dorsin, and Peral. However, if you add a quadratic term in the gradient, like this, in the left-hand side, then this problem now has a solution for any lambda and any positive function f in L1. This is a result by Abdelawi, Peral, and Primo, and moreover, they went further, and indeed they proved that if you add a q power of the norm of the gradient, q here between 1 and 2, then if g is an admissible weight, which means that this infimum, which is related to the infimum of the function f that I showed you before, if this variational quantity is positive, then there is a solution of this problem for any positive f in L1 and any lambda greater or equal than 0. Okay, so in this way, if you have first order terms in an equation like this, then like that term produces a regularizing effect and allows for the existence of solutions in the equations. Okay, so now let's go to the main model that we are going to discuss. First, I will discuss some results in the local frame, and then I will set the fractional model and the main results of the talk. So let's take first this equation, okay, this local equation, where now here we have a measure, and the equation is considered in Rn. Okay, so let's see now a necessary condition for existence of solution, which is related to the Riesz capacity. So in order to motivate the relation between existence of solutions and capacities, we are going to do some little calculations. So suppose that you take a compact set in Rn, a smooth function h compactly supported, which is greater or equal than the characteristic function of E, of the set E. Then if we called P the conjugate exponent of Q the power of the gradient here, this Q is assumed to be greater than 1 by now. And if we test this equation with the h to power p, what we get is this equality here, okay? So now, if you take the measure of the set E, so the measure of the set E is less or equal than h to power p with respect to the integral with respect to omega, to the measure. And here, we can solve in this equality for that integral, and we can apply a Hellner inequality here in this part in order to get this difference here. And now in this part, we can use this numerical inequality to get this final estimate. So now if you take the infimum over all function h that satisfy these conditions here, what we get is that the measure of the set E is controlled by indeed the Bessel capacity of the set E, which in turn can be controlled by the Riesz capacity. Okay, I will define the capacities later, but what we have here is that we need some control in the measure in order to have solution for the original problem. So this is again related to the presence of first order terms in equations and the restriction in the size of the source. So this is another version of the restriction of the size in the source. So these kind of results were deeply studied in Hanson, Massey, and Versbinki, and indeed they prove that this condition over here is sufficient also to get existence of solutions, okay? Okay, so let's go now to our problem, the fractional version of the Riccati equation. So we are going to consider here the fractional equation in Rn. So we look for global solutions for s greater than 1/2. So here that is because we want the fractional operator to be the leading operator in the equation. We look for positive solutions in Rn that vanishes at infinity, okay, that vanish at infinity. So here we are going to assume that omega is a non-negative Radon measure with compact support in Rn, and the power Q here will be greater than this like critical exponent in some sense, which is n over n minus 2s plus 1. So I will show you later why we need this restriction, but it is also connected to some relation between capacities, the Bessel capacity and the Riesz capacity. Okay, so before showing the main contributions on that fractional problem, I will introduce some preliminaries and notation. So by S of Rn, I will denote, of course, the Schwarz class of functions. The fractional Laplacian for Schwarz functions may be defined by following the Fourier definition, which is this one, or the integral definition with a constant here so that the two definitions coincide. So here the integral is taken in the principal value. Also, some spaces which are connected with the fractional framework, Ls of Rn, this is the set of functions, locally integrable functions in Rn, so that you can control in some way, in this way, the tail of the function. And then here we have a type of a kind of a Schwarz class, again adapted to the framework, to the fractional framework. So we have this space. And here we have some comments which will be useful for the definition of solution that we are going to consider for the fractional problem. So first of all, the set Ls of Rn, this space, is a subset of the topological dual of this set here. So moreover, if you take a Schwarz function, then its fractional Laplacian is in this space, okay? So we may define for functions in Ls of Rn, the fractional Laplacian in the sense of distribution as follows, okay, for any function phi in Schwarz function, for any Schwarz function here. Okay, so let's see the notions of solution that we are going to consider here. So first, if you have just the measure on the right-hand side, we say that the function u in Ls of Rn is a weak solution if this holds for any Schwarz function. And if you take now the equation with the nonlinear first order terms on the right-hand side, we say that u in Ls of Rn and in W1Q log of Rn is a weak solution if this holds for any Schwarz function, okay? So these are the notions of solution that we are going to consider. So before showing the main result, let me remind you the definition of Riesz potentials. So the Riesz potential of order alpha, alpha between 0 and n, is defined in this way for any locally integrable function g, such that this condition is satisfied. Okay, so we need this condition in order to get that this potential is finite almost everywhere. And for a non-negative measure omega, we define the Riesz potential in a similar way. And again, you can impose a condition like this in the measure in order to get that this potential is finite almost everywhere. But here we are going to consider measure with compact support, so we are fine here. And also for alpha between 0 and n and q greater than 1, the Riesz capacity of order alpha q of a set E is defined as the infimum of this norm, so that the Riesz potential of the function u is greater or equal than the characteristic function of the set E for u non-negative and in LQ of Rn. There are several equivalent definitions of capacities, or at least that they coincide to each other over compact sets, but I will take this version of the definition of Riesz capacity. Okay, so the main result that I want to show you is a result with Maria Laura de Borbón, which is also, she is also from Argentina. She's a collaborator. And suppose that S is greater than 1/2, less than 1, Q greater than this critical exponent, and indeed will be greater or equal than 3 because we are not using log potentials, but I will impose this condition again. And suppose that there is a constant C, so that we have this relation between the measure omega and the capacity. So the capacity of order 2s minus 1 and q prime. So if you recall what I showed you before for the local case, so here we have the capacity of order 1 and q prime. That is the case where s is 1. So we are imposing a similar condition that in the local case. So suppose that this is true for all compact set E in Rn, then the equation, the fractional Riccati equation in Rn has a non-negative weak solution in W1Q log of Rn, and moreover, U has this representation in terms of the Riesz potential. Okay, so this is the Riesz potential of order 2s. And this representation will be useful in order to get some estimate of the solution U in terms of the source omega. Before discussing the sketch of the proof, I will provide this equivalent condition for the relation between the measure and the capacity. So this is a result by Masia Persvinki. So this condition for all compact set E in Rn is equivalent to the following inequality for this nonlinear potential. So observe that this inequality allows us to simplify a lot the left-hand side and to write just the Riesz potential of order 2s minus 1 of the measure omega. Okay, just to give a sketch of the proof, the starting point is to solve the problem without the first order term. So if you define U0 as the Riesz potential of order 2s of the measure omega, then U0 has the right regularity for these problems, and indeed it is the solution of the problem with omega in the right-hand side. Moreover, its gradient can be controlled by the Riesz potential of order 2s minus 1 of omega, and since q is greater than q star, this potential is in LQ of Rn. So here we used strongly this assumption. Indeed, this relation here holds for any function f in L1 of Rn. Okay, just the inequality. So we can apply this inequality to the function gradient U0 to power q. This is in L1 of Rn. So by this inequality, we have that the Riesz potential of order 2s of this part can be controlled by this guy here. And the gradient of U0, as you see here, can be controlled by the basically this potential. So what we have is this guy here. And since we are imposing the condition between omega and the capacity, this is less or equal than just the Riesz potential of order 2s minus 1 of omega. Okay, this is by assumption. So if you define B as this potential here, what we have by the above inequalities, that B is in Ls of Rn and also satisfy this equation with the nonlinear first order terms, gradient U0. So what we have here, so up to now we have that the fractional Laplacian of this sum is the Q power of the gradient of U0 plus omega. So we are like close to what we want, but this is not exactly the solution of the problem. So what we are going to do is to construct a sequence. So the sequence will be this one. So observe that when k is 0, what you get here is just b plus u0. So the starting point of the sequence is b plus u0, and then when k is going to infinity, what we expect is that uk converges to some function u, and the function u should be the solution of the problem. Indeed, if at least formally you take the limit here as k goes to infinity, so what you get is that u is the Riesz potential of order 2s of its gradient to power q plus omega, which is the representation formula for the solution. And in order to prove that this sequence converges, so first we can control the gradient by this potential, which is in LQ of Rn, again, since q is greater than q star. So these gradients are in LQ of Rn. And also if you compare the gradient of a term of the sequence with the gradient of the previous one, this difference can be bounded by some delta between 0 and 1 to power k plus 1. So here, from here we can get the convergence of the uk to a function u, and indeed the gradient of the function u is in LQ of Rn, since its gradient satisfies this relation here. Okay, so now one can take the limits here and prove the representation formula for u, and that u is a solution indeed of the original equation. So what happens with the converse of the result? That is, if you have a solution of the problem, what happens between the measure and the capacity? So here we have a partial converse of the result, because what we could prove is the following. Suppose that q is greater than q star, and that we have a global solution of the equation, but the solution lies in W1Q of Rn, not only in W1Q log. Okay, I will say something about this later, the regularity of U. But suppose that you have a solution with this regularity. Then the measure omega does not charge set of Riesz capacity of order 2s minus 1 and q prime 0. So that is, the measure is absolutely continuous with respect to this Riesz capacity. So it's not the exact result that we wanted, because we wanted the inequality between the measure and the Riesz capacity, but this is something, okay? And in order to give an idea of the proof, suppose that you take a smooth approximations of the function u, compactly supported, and take a smooth function in Rn with compact support greater or equal than the characteristic function of a set E. E here is a compact set. So then the measure of the set E, we want to prove that this guy is 0 if the capacity of the set is also 0. So this measure can be controlled by this part of the equation, because I mean, if you test here with the function phi, And you can delete this term because this term will be negative. So you just have this part over here, and then you can approximate u by these uk, which are compactly supported. Use some relation between the fractional Laplacians, and just perform a Hölder inequality. And here we have the LQ norm of the fractional Laplacian of order 1/2 of u. And by the continuity of this operator from W1Q into LQ, this quantity here can be controlled by the norm of the gradient of u in LQ of Rn. And this part here is related to the norm of the function phi in a Bessel space. So if you assume that the Riesz capacity of a set is 0, then the Bessel capacity of the set is also 0. That is because Q is, the assumption that Q is greater than Q star is also used here, because this relation between capacity is valid under some relation between the order of the capacity, which is true here. So the Bessel capacity is 0. So that means that you can find a sequence of functions in this space. I didn't define this space, but it's just a Bessel space. So that these functions are greater or equal than the characteristic function of the function of E, of the set E. And they goes to 0 in the norm of this space. So if you use this inequality here for the sequence, and then take k going to infinity, what you get is that the measure of the set is 0. So we prove the result. So we have, it's not a characterization of solutions as in the local case, but we have something very, very similar. So I also want to show you some related results in bounded domains. So in a paper by Cheney Veron, they prove that you have solutions of equations very similar to our problem, but in bounded domains, where the function g here has this growth. Observe that the power of the growth is less than the critical exponent that we consider in the unbounded case. Okay, so and they get solution. This nu is a measure, and the function g. The function g can be in the right hand side as a positive function, or in the left hand side as a positive function as well. But here I just consider the case of g a positive function on the right hand side. And recently, Ireneo and Boumedian, they prove in bounded domains that if you have a problem like this, which is related to our problem, but in bounded domain, then if lambda is sufficiently small and g is sufficiently integrable, then there is a solution of this problem for q greater than 1. And in Rn, they prove something related to our result. If q is greater than q star, and if the function f is in Lm with m sufficiently large and non-negative, and if it satisfies this relation between the Riesz potential, then you have a solution of this problem in Rn, and the solution is in W1Q log of the whole space. So this result is like a version of our result, but it's for function f in Lm with m sufficiently large. So we have here measures, but our measure has compact support, so there are some differences between the results. So there are some estimates that we can get from our result. So if omega is a measure with compact support, we can get the following. So the function u is between the Riesz potential of order 2s of the function omega in this way, so it can be controlled from below and above by the potential. And also the gradient of the function u of the solution can be controlled by the Riesz potential of order 2s minus 1 of omega. So if Q is greater than n over n minus 2s, what we get is that the regularity of U is W1Q in Rn, so in the whole space. So I told you that for the converse of the theorem, or the partial converse of the theorem, we need a solution, a global solution in W1Q of Rn, and not only in W1Q log. So here we have that if Q is greater than this guy here, we indeed get solution in that space. Moreover, since we have this upper bound here in the function U, we have that U vanishes at infinity. And if we use the lower bound for a measure omega whose compact support also has positive measure, then the function U is positive everywhere in Rn. Also, the function U is finite. We can get that the function U is finite everywhere in Rn. And here maybe it's a little small, but I can tell you. So we can get some estimate of the norm of U and its gradient in Marcinkiewicz spaces, okay, with respect to this measure here, which appears in the fractional setting. And the control is given by the norm of the measure omega in the space of measures. Okay, so we can control U and its gradient. And now if you take a function, an integrable function, let's say omega is now a function f with f in Lm, non-negative with compact support, then according to the values of m, we can get further regularity. For instance, if n is 1, we can control the measure of the level set of the solution in terms of the L1 norm of the function f. Okay, these are consequences of the same estimate for the Riesz potentials. Also, if m is greater than 1 and less than n over 2s, we can control the LR norm of the function U in Rn in terms of the norm of the function f for any r in this interval. And if m is between 1 and n over 2s minus 1, we can control the norm of the gradient in this range. And if you increase m, like m equals n over 2s, we get that the solution U is in any LR space for any r in this interval. And also in the Sobolev space, we can get the same conclusion if m is n over 2s minus 1. And if m is greater than n over 2s minus 1, we get that the gradient of the solution is Helder continuous in Rn. Okay, so this, again, they are consequences of this estimate here. Also, we have a representation for the gradient in terms of Riesz potential, and they are also consequences of the regularity of the Riesz potential in the theory of potentials. So here there are some references. This talk was based, the contribution, which is the second part of the talk, was based in this work with Maria Laura de Borbón. Also, there are some related results in this paper with Abdelawi and Peral. And also there are, this is just some references, they are not, it's not an exhaustive list of references, but for potentials and capacities, this is a good source. And the book by Lankov is a nice presentation of the theory of potentials. Okay, so I will stop here. Thank you for your attention.